So in this video, we'll look at a couple of more exercises on the application of L'Hopital's rule to the calculation of limits. And let's look at the current example. You are looking at the product of two functions, is x times sine of 1 over x, and I try to take the limit x goes to infinity. And as a first step, we can replace x by infinity conceptually to check what's happened to the product. So let's say x is infinity conceptually now. X times sine of 1 over x becomes something like infinity times sine of 1 over infinity, and 1 over an infinitely huge number conceptually is very close to 0, so you can think of it as sine of 0 for the second factor. Of course, the first factor is infinity, so sine of 0 is 0. So now it looks like infinity times 0, which is an undetermined item. It is undetermined, and it means that we don't know the answer yet. We have to rely on the L'Hopital's rule, so we have to find a way to do it by making the product look like a quotient first. So instead of looking at the function as a product of two things, we can keep the sign of 1 over x at the top unchanged, and to move the x to the denominator, so we have to revert it, right? Which means instead of looking at the x factor as a multiplication, we can divide the sine function by 1 over x, and now you see it's a quotient now, and it is still undetermined, should be. So it means we can apply the L'Hopital's rule, and it means that you have to differentiate the top and bottom separately. And for the bottom, is the derivative of 1 over x, so it becomes minus 1 over x squared for the bottom. And for the top, it's the derivative of sine of 1 over x, and becomes cosine of 1 over x if you differentiate the function sine with respect to 1 over x. But it's a chain rule application. You have to multiply the cosine of 1 over x with the second factor, which is the derivative of 1 over x. So it becomes 1 over minus x squared. And this part is the derivative for 1 over x. I'm using a chain rule application for the numerator, so we can keep going on this calculation. So please check that what you have in the denominator can be cancelled out with the factor in the numerator. So after cancelling the common factor, we are actually just looking at one single factor, which is cosine of 1 over x. And let's check what's happening. When x is conceptually the same as infinity, you are looking at the function as cosine of 1 over infinity. And please recall that 1 over infinity is conceptually the same as 0. So it means you're actually looking at cosine 0. So cosine 0, of course, is the same as 1, which is the final answer to this problem. And let's look at one more problem. So please look at the current problem. We're trying to resolve this limit. And you see now the power itself is a function of x. So it is somehow tricky to deal with such a problem. And let's replace it by 0 to see what's happening for the function. So when x is 0, the fact is that now the function looks like the base is 1 plus 0 to the power 1 over 0, right? So it means conceptually it's the same as 1 to the power infinity. And please don't think that it is 1. It is actually not 1. And you can actually check it quite easily by computing this function by using a very small value of x. Let's say you use x equals 0.001. You will notice that it is not a value close to 1. It gives you a sense that this one may not be 1, right? It may not be. So actually the fact is that whenever you look at 1 to the power infinity, we call this item undetermined. So it means you don't know the answer yet. In that case, usually we have to try some ways to do the L'Hopital's rule, and let's do it here. But now the power contains a function of x, right? And let's do it this way. We let y equals 1 plus x to the power 1 over x, and to cancel out the strange power, which is a function of x, I can apply ln to both ends. This strategy is always quite useful when the exponent contains the power of x. So because the ln function has a special property, you can pull out the power. The power is 1 over x times ln of 1 plus x now for the right-hand side. And now, instead of looking at the original limit problem, I can try to take limit of the current case. And of course, this problem we are looking at is not the same as the original problem because I have taken a ln one time already. But anyway, let's do this calculation first. When x is 0, let's see what's happening. When x is 0, we are seeing something like ln of 1 divided by 0, which is 0 over 0, which is the undetermined case, which gives us a chance to use the L'Hopital's rule. It means that we can differentiate top and bottom separately. So for the bottom, it's going to be 1, which is the derivative of x. And for the top, it should be the derivative of ln of 1 plus x. And ln of 1 plus x, when we take the derivative, it becomes 1 over 1 plus x. Mathematically, we need to multiply it by a term, which is the derivative of 1 plus x, but it is 1, right? So now I have applied the chain rule to the top for the derivative of ln 1 plus x. So anyway, the calculation for differentiation of the top and bottom is done, so we go to the next step. So you see now the limit problem becomes 1 over 1 plus x. Of course, we can replace x by 0 now. It is not undetermined anymore. So the answer is 1, right? The answer is 1 for this limit quotient. However, it is not our original problem. So we have to think a little bit about that. So let me write it down this way. So our calculation implies that we got the first line done. So the limit x goes to 0 for ln of y is the same as 1. But the actual answer we want comes from the second line. And I skipped some concept a little bit, but just to let you know that for the ln function, you should have learned this property. Please look at the red box on the right end. If you have something like ln of x equals a, x is actually the same as e to the power a. And we are looking at a limit problem. So there are some issues about the continuity and etc. But because the ln function behave quite well, it is smooth, it is differentiable, etc. So I skip some steps. But just let you know that we can make use of what in the red box. So we can write the answer down for the limit x goes to 0 for the y function. Because we have the limit x goes to 0 for ln y already. So we expect that the answer based on what we have here should be just e to the power 1, e to the power 1. So which is e. And please recall the meaning of e. Mathematically, it is the same as 2.71 something. It means what? It means our answer to our original problem is that the limit x goes to 0 for the 1 plus x, the whole thing to the power 1 over x, is actually the same as e. And e numerically is 2.7 something. So it means what? It means if you try to understand this by approximation, you are free to replace x by a very small number. And in that case, when you do the calculation by calculator, you would notice that you get a number very close to 2.71 something. And it's almost the end of the video. Just to let you know the following facts. The L'Hopital's rule in general is used to deal with the limit where it is a quotient and it looks like an undetermined form. And for a quotient, the most common undetermined forms are these two, and we have seen both of them already in this video and the last one. And if it is not a quotient, sometimes we see some other undetermined form. For example, as a product, it can be something like this. And just in the last example, we saw another undetermined form, which is 1 to the power infinity. For all these cases, we expect that we have to try to maybe somehow use the L'Hopital's rule to help us find the answer to the limit problem. And that's the end of this video.